Well, this is John Black, super chemist. We're going to talk about Planck units. Um, you know, he devised these units, I guess, to start these natural units, right? Natural units are stupid. Don't ever let no one get, it's communism. They just want you to be stupid. They want you to take all the constants out of all the equations so no one knows what's going on. You know what I mean? How can you know what's going on if you take out all the constants and make them a number one? You know what I mean? No one will put the constants in, and then no one will know what's going on. It's stupid. Don't do it. Planck units, it's a system of measurements defined exclusively by four constants. Okay, you got your big G, gravitational constant, right? Here's your units. You got Planck's constant reduced. That means the h bar, right? And it's in joules per joule second per rad, right? How do you change it into the Planck's constant? Here it is up here. Here's the reduced one, right? It has the bar on it. You just take it and multiply it by 2 pi rad per cycle, because how many rads are in a cycle? Or, well, 2 pi 6.28, right? So all you have to do is take 6.28 times your your reduced Planck constant, and you will get the rad here and the rad here. They will cancel out, and you will have joule second per cycle. And you'll notice that the H, right, is joule second per cycle. They're both 10 to the negative 34th power, right? But just notice, this one here is the reduced one, 1.05. All you have to do is multiply it by 6.28, which is 2 times pi, right? Because 6.28 times 1 is 6.28. But we had a little bit extra there, so you can see it's just 6 times more. That's it. It's the same thing. One's in rads and one's in cycles. H is this, joule second per cycle. If you want h bar, you divide it by 2 pi, because the 2 pi is 2 pi radians per cycle. You know what I mean? You're going from cycles to radians. Then we got Boltzmann's constant. It's joules per Kelvin. And then the speed of light, which is meters per second. The speed of light is not, it is a constant. To be using it in this fashion when he's saying universal constant, no, that's stupid. Anyone who uses C, sometimes you do have to use C, but most times C does not represent C, okay? It's just the speed of something. That's like me putting 55 mile an hour on something because I see it on the signs, driving around. No, that's not a whatever, okay? So we're going to go over just 4 of the constants. 4 of his units, right? Because he's supposed to be talking about the smallest unit of that unit. You know what I mean? Like you got length, time, energy, mass. It's supposed to be the smallest length, the smallest time, the smallest this, the smallest that. Okay? And you can see right here, he's got energy. Look at this energy. 10 to the 9th power joules. That's like something. That's like a tank full of gas. You know what I mean? It's not nothing big or nothing small. And then you got mass here. What is this? 10 to the negative 8th kilograms? That's like, 1 flake of cereal. You know what I mean? How is that a Planck unit? I don't even get that, okay? Then we'll go into my Planck units. It at least makes sense. Okay, so first of all, how did he get all these, these Planck length, Planck time, and all this stuff? He basically used these 3, and I guess if you want to use Boltzmann, he used Boltzmann for some of them, you know what I mean? But it's just about temperature, so he didn't use that much. He basically just used these 3 constants. G, big G, Planck's reduced constant, and the speed of light. The speed of light ain't even it shouldn't even be in there. Now originally he used Planck's constant instead of the reduced Planck's constant, but you can see I'm using reduced Planck, the modern version or whatever, right? So I want you to look at these. These are the 4 formulas that he's using, right? He's going to plug that first one in. This is for the, the length of time, energy, mass. But I wrote them down right down here. These are the 4 formulas that he used. And all the stuff in blue is identical on all 4 equations. The only thing that's different is on these first 2, they have the C's on the bottom and the G on the top. And then the last 2, you got the G's on the bottom and the C's on the top. It's reversed. And one other thing that's different, right, is these to the powers. The power of 3, this one's the power of 5, this one, actually this one's the same, it's the power of 5, but they're inversed. And of course this C doesn't have a power at all. And none of the other ones do either. He only puts the, the exponential stuff on there, on the C's. He doesn't put them on any of the other things. But this is ridiculous, okay? First of all, C, he shouldn't be even using C. That's ridiculous, okay? So he's basically just using G and H. It makes no sense whatsoever. And then you look at these energy, I mean, and this mass, those are a joke. Those are literally a joke, okay? It's just got those 3 things, and then he puts them in these square root things. And he acts like just because he canceled out the units that he did something, okay? But on these first 2, okay, I'm going to tell you what he said, because he actually makes sense on these first 2. My Planck energy and Planck mass is totally different than what he has down there, and we'll go over it in a second. So why does it make sense on the first ones? Well, let's go first to the Planck length, okay? Why is there a Planck length? What does that mean? There's like 3 or 4 ways to describe this. I'm just going to go the easiest route, okay? Let's say you have a particle like this proton here, right? If you want to look at it, take a picture of it, you got to throw some photons or something at it, electrons, something, to capture that image, right? It's too small for you to see it. But anyways, whatever you throw at it, right, whatever photon or whatever you put, the wavelength, see down here, you can see, right, the wavelength here has to be at least as small as the thing that you're trying to take a picture of, right? So see, the photon is a little bit slightly bigger than the proton. But let's say you're going to even smaller, to like this electron. Now you need something like in a Blue Ranger. I'm making up colors here. But you need a smaller wavelength, right? That's comparable to the electron. You can see they're about the same size, right? Well, what about over here? Now you got a little purple dot thingy. Look how short that wavelength is. You see where I'm going here, right? Now you got this little, you can't even barely see it. It's a dot. And underneath I did a whole bunch of, waves. But one of these waves, because there's a whole bunch, right? This black part here, one of them is about the size of that dot, okay? And my whole thing is, though, is if you keep getting smaller and smaller and smaller, that you want to look at something smaller and smaller, that means you can see the frequency went from red to blue, purple, well, and now black. But this is like getting up into ultraviolet, right? You're getting more frequency, you're getting more power, right? If you keep doing this, right, you're going to keep adding more and more power, more and more higher frequencies, and you're going to end up creating a black hole, okay? This is basically the escape velocity, right? And if you take this escape velocity and you rearrange it, you know what I mean? And so that the radius is over here, and the velocity is now c, right, instead of v, because that's the velocity that we're going to use. And basically, so we set the speed of light. This is escape velocity right here. We set the escape velocity at the c, and we know that that's a black hole. If you have a escape velocity at c, then you are a black hole at that point. Okay, I mean, so if we figure this all out and do the math, we can figure it out. But basically, what he did was he just came over here, right? He wants Planck's length. He's got this formula, so he just plugged everything in. Here's G, here's reduced Planck's constant, and then he cubed light and put it in his formula until he got this R, right? Because that's the Schwarzschild radius. See, this radius is of the electron, or whatever, what I mean, you're talking about, right? And the radius is set to make a black hole, right? Because you got it set at C here, right? You can see how this formula here, where he's getting the Planck length, is very similar to the escape velocity, the escape velocity equations. But basically, that's all he did, was he went smaller and smaller till he could see when he would make a black hole, right? And then when he figured that out, he goes over to here and he just plugs these constants into this formula here, right? And this is what he gets. He gets 1.616 times 10 to the negative 35th meters, right? Now, does this mean that, there's something weird going on at this Planck length, right? This 10 to the negative 35 meters. No, it doesn't mean it's just magic. It doesn't mean that there's just because you can't explain what's going on there, doesn't mean you make up stories and fairy tales, okay? It doesn't mean that there's no, beyond a Planck length, if it's smaller than a Planck length, then there's nothing really going on there. Like, it doesn't exist. It exists, okay? Just because you can't see something doesn't mean it don't exist, okay? It doesn't mean that there's no, all the physics just doesn't exist. The physics still exists, okay? Stop acting like everything is magic, okay? It just means that it's so small. I just explained why. That you have to have so much energy with your light wave or your electron or whatever you're throwing at them, right? To take a picture of these small objects. You keep going smaller and smaller, you're going to create a black hole, man. You can't go any smaller, so you can't see that. You can't see that's something that small. So if you had too much energy in the same little place, you know what I mean, at 10 to the, I'm just making up numbers here, but about 10 to the negative 13th meters, when your wavelength is that small, you'll have enough energy if you concentrate it, you know what I mean, to start making an electron, you know what I mean? At 10 to the negative 34 meters, you'll have enough energy, from the frequency, trying to look at stuff, right? That at that point, right, at that distance, 10 to the negative 34 meters, the gravitational force and the EM force will be equal at that point, okay? Normally, the gravity doesn't play much, but when you're this close, 10 to the negative 34th power, meters, gravity is just as strong as the EM force, because more mass, because you'll be creating mass at this point, and the more mass you make, and you make a little bit of mass, and then you make a Schwarzschild radius for that mass that you just made, you are going to make a black hole, okay, at that point. And it's not as much about making more mass, it's more about density, you know what I mean? I believe in this length, it sounds logical, right? Makes sense, right? And there's 4 or 5 other ways you can describe this, how you can't go down that, this, once you get to this length, things break down if you want to actually look into that length, you know what I mean? Because you need something, like I said, that has a very high frequency, a lot of power and energy. It's going to just make a black hole. So how do you get from the length to the time? Okay, this is the first time that I'm going to say that you should use the C constant, okay, right? And you divide it into this, right? Because it's going to be meter per second, but that second's going to go up on top The 2 meters will cancel out and you'll be left with seconds. And you will be left